In this video, I'm going to talk about the periodic table and about how people come to know that there are protons in the nucleus of an atom. Let me start by writing out, just from my own experience, some of the more familiar elements that I think would be helpful in understanding physics. I'll start with this very rough sketch of a periodic table, which you can find if you Google, if you do an internet search. Now, I'll start with H here. Now, the idea of a periodic table is that the atoms of the elements are arranged in order of the number of protons. But historically, when the periodic table was first discovered, the atoms are largely arranged in order of their atomic masses, which over the past few hundred years has been measured very accurately. Well, I said largely, but not completely. I'll say why in a moment. So, starting with hydrogen, the next element is helium. Okay, so the atomic number goes in the same order as the ordering on the periodic table. The next one is lithium, and then there is boron, there is carbon, nitrogen, oxygen, fluorine, neon. Okay, I'm just writing out the symbols, so if you're not familiar with chemistry, some of them might look quite strange, but bear with me. So that's sodium. I'll just read out the words as I write them. It's magnesium. It's aluminum. You might hear some familiar elements. Aluminum is quite familiar. Silicon is very familiar nowadays. It occurs in all computers. Phosphorus is an essential mineral in our body. Sulfur as well. And then chlorine, we drink it every day in our tap water, and highly poisonous. Argon, used in light bulbs. Potassium, again an essential mineral. Calcium, very important for our bones. Somewhere around here is iron, which is very important for everyday life and technology. And there's nickel, copper, used in coins, zinc, okay, and then just below copper is silver, okay, used in again money and a lot of modern electronic devices, and gold as well. It's gold. And then we have tin. Tin, of course, if you have ever eaten canned food, a can of sardines, that's what the tin is made of. Lead. Okay, lead. Let's see. Now there is down here bromine, okay, and iodine. If you ever had a cut, you might have used iodine solution to rub on your cuts to kill the germs. Okay, so these are more or less the more familiar one, and there are others which are less, maybe a bit less or a lot less familiar, which I shan't write down. So this is arranged in order of the atomic number, in the sense that this is the atomic number. Say for hydrogen will be 1. Let me write it down here. So 1, that's 2, 3, so 4, and then 5. Carbon atomic number 6, 7, 8, 9, 10, 11, and so on. Okay, and so on. So it is arranged in this order, and and it is grouped in this way because in each group the elements have very similar properties. Like when it's in a vertical group, these are metals which are very reactive. I'll just pick out a few examples. In this column, these are called noble gases. So these are gases that are very, very unreactive. Okay. Now fluorine, chlorine, all these are non-metals which are very reactive. Okay, and chlorine is poisonous, used to kill people in the Second World War, and today it's used to kill germs by adding small amounts into our tap water and in swimming pool. And here you have oxygen, sulfur, which oxygen is important for life, and then nitrogen, phosphorus, and so on. But those that are down here have properties which are less similar. Okay. So in any case, if you're doing physics, the way we could use a periodic table, we usually can use it to get two main pieces of information. One is the atomic number, which will tell us the number of protons in an atom of the element. Like fluorine, if I look at fluorine and the atomic number is 9, or the ordering in the periodic table is number 9, then it means that there are 9 protons in a fluorine atom. Now the other piece of information which we can get from here is the mass number. So the mass number, for example, you'll find that for mass number, or to be precise, the relative atomic mass. So for carbon, it would be 12. Now it depends on what periodic table you look at. If you look at a more accurate one, or one that gives you more accurate values, you may find that the mass number or relative mass given for hydrogen is 1.008. Okay, and for helium is 4.0026. Almost 4, but a tiny bit more. Okay, and for chlorine, you find that the mass number is actually write it up here, 35.5. So just to give a few examples. Now, these numbers here, now I've previously explained how, say if we look at, think of the mass number of an atom, is basically the total number of protons plus neutrons. Number of protons plus neutrons. Okay, but so what does it mean if I have 35.5? Does it mean that I have half a neutron? Well, actually what happens is that with chlorine, remember in the last video I've talked about how atoms can have different number of neutrons. Right? An atom can have different number of neutrons, and with chlorine, for example, chlorine can have a mass number of either 35 or 37. Okay, so it means that some chlorine can have 2 extra neutrons compared to the other chlorine, and the chlorine atoms that have a mass number of 35, they occur naturally, and in say chlorine that is present in, say, sodium chloride, the common salt that we eat every day, contains chlorine atoms, or in reacted form, of course, with sodium. Otherwise it's poisonous. And the chlorine atoms in the common salt that we eat, or in the dissolved in the tap water that we drink, contains let's see, 75% of chlorine 35, with mass number 35, and it contains 25% of chlorine 37. Okay, so the 35.5 that is given in the periodic table, that you'll find in the periodic table, is actually an average of 35 and 37. Average not as in simply adding up 35 and 37 and dividing by 2. Okay, we have to multiply the 35 by 75%, because there are 75% means that there are more of this mass number than this number. So we have to multiply 35 by 70% and then 37 by 25%, and when you add those up, you get 35.5. So that's why we get decimals. Okay, that's why we get decimals. 35.5. Like this. So the reason why chlorine, the chlorine mass or relative mass given in the periodic table is 35.5 is because it has atoms that have different number of neutrons. Now these atoms with different number of neutrons have a name. They have a name. They're called isotopes. So the isotope, for example, this is one isotope and that's another isotope. Now in the last video I've used the word nuclei to describe a particular nucleus, a nucleus that has a particular number of neutrons and protons. Okay, so the word isotope is kind of closely related to the nuclei, except that the isotope would refer to, say, the whole atom or elements, and not just the nucleus. Atom as in including the electrons, or when you have lots of atoms of the same kind of nuclei. Okay, so we call these isotopes. Okay. So we now understand why there are these decimals, but not all the decimal places that you see on the periodic table for the mass of the element, not all of these are because of are due to having different isotopes with different number of neutrons. For example, for hydrogen, it turns out that the hydrogen is mostly there are hydrogen which have one or two neutrons as well. So it's also possible for hydrogen to have different isotopes. Okay, but there is another reason why the mass number of hydrogen would have this decimal place. Okay, and it is because of something called binding energy that I'll talk about later. So I'll skip over this for now. Okay. So as I was saying, for many hundreds of years, maybe 300-400 years, until the beginning of the time when the beginning of 1900s, when the Bohr model and understanding of the atoms start to happen. Before that, these elements were arranged mostly in order of the atomic masses, with some exceptions, because people can measure the masses of the atoms, or at least the masses relative to each other quite accurately. So how did the idea of or the knowledge that there are such a thing as protons inside the nucleus come about? Okay, it comes about from mainly two. Well, that's a bit simplistic. Okay, it comes about from a number of discoveries. Now, I'm just going to mention maybe 3 of them that we would study. We have to study in detail for A-level physics. Okay. So remember how I was talking about the Plum pudding model, which was proposed by J.J. Thomson to describe an atom soon after he discovered the electrons. And so after not long after that, Rutherford discovered that an atom has a nucleus where most of the masses are concentrated and the electrons go round and round. Okay, and from Rutherford's discovered the nucleus of the atom. We have Niels Bohr, who came up with his idea that if you think about the hydrogen atom, okay, with as a nucleus with an electron going around it, okay, and where the electron can only take certain energy levels, then Bohr was able to explain the line spectrum. Remember the line spectrum? Line spectrum, which we saw in an earlier video, the one of hydrogen, line spectrum of hydrogen, the one with a red line, okay, light blue line, a blue line, and a violet line. Okay, the line spectrum of hydrogen. So Bohr explained that by using things like electrical attraction between electrons and protons. Okay, and at that point, Bohr started the idea that in the hydrogen atom, right? You know, for the electron, the electron has a negative charge, and it was discovered by J.J. Thomson some years before that, and Bohr simply assumed that the nucleus has a positive charge of the same magnitude. So if the electron is minus e, the proton, the nucleus of the hydrogen atom is plus e. So that's the protons. That would be the charge in the nucleus. So, but at that time, the idea of the proton was not there yet. The nucleus of the atom, of the hydrogen atom, was just a nucleus. People just thought of it as a place where most of the mass of the atom is concentrated, and that it has a positive charge. People have no idea what's inside and what kind of particles, or if there are any description of particles inside. So just no idea. Okay, no idea. Just a mass and a charge is all people know. No idea about protons or neutrons, right? And very soon after Bohr, these are the early 1900s. The period we're talking about, the period between 1900s and 1920, right? During this period, so we have Rutherford's nuclear model, discovery of the nucleus, Bohr's calculations, which explain the line spectrum, giving us a detailed understanding of how energy is changes and how an atom might be described. And then shortly after Bohr's theory and explanation, there was Moseley's. If you remember my video on characteristic X-ray, so Moseley, who studied the characteristic X-rays, okay, the one, you know, the lambda, the one that looks like this, with a peak there and a peak there, you know, there's a with the K lines, K alpha and K beta lines. So what Moseley found was that the energy, the energy of, say, one of these lines, say the K alpha line, if we plot the energy against the atomic number, right, Moseley used Bohr's equations, okay, to calculate the energy of this K alpha line. Let's say that's the energy. So he calculated the energy for the characteristic X-ray spectrum. This is the X-ray spectrum. For each of these elements, okay, and what Moseley did was he calculated it using the same picture as Bohr's atom, but instead of just having the charge of E at the center, Moseley used a charge of Moseley also used the same picture as Bohr, so a nucleus with electrons going around it, okay. But what Moseley did was, instead of using just a plus E like Bohr did for the hydrogen atom, Moseley used the atomic number times E. Actually, Moseley at that time wasn't sure whether he should try using the atomic number for the nucleus or the mass number. Right? There's really no reason why he should use one or the other. Okay, and he probably discussed with Bohr, and Bohr thought that it should be the atomic number. So in any case, Moseley tried using the atomic number for the number of charges in the proton, put it into Bohr's equations to calculate that Bohr used to calculate the line spectrum for the hydrogen. So instead, Moseley used the same equation to calculate the peak energies of the characteristic X-ray. And what Moseley found was that they agree very well with experiments. Okay, so that was as I have described in my videos on characteristic X-ray. So the calculation line, the calculated graph by Moseley, goes through all the measured points, right, obtained from the measured energies of the X-ray spectrum. So this sort of further clarify or the idea, give people more and more clues about what is inside the atoms, so that it seems that it's easy to imagine from then on that there are probably these particles, you know, which are positively charged. And since there are always this whole number of positive charges, it seems reasonable to think that there are probably particles inside the nucleus, and each of these has a positive charge. Okay, each of these have a positive charge. The only puzzle at that, one of the puzzles at that time was why this number is this atomic number is about half the value of the mass number. Like if you look at helium, the atomic number is 2, but the mass number is 4. So at that time, people didn't know about neutrons. Okay, that came a few years later. So, but they were still they were still at the stage of learning more and more about things that will lead on to the idea of a proton. So eventually, what finally made it clear that these particles that there are actually these particles, which are later called protons, comes from an experiment which Rutherford did, an experiment in which he actually carried out a nuclear reaction that produced protons. So I'll talk about that in the next video. Okay, but in this video, what I hope is that by tying together the knowledge that was developed over a few hundred years based on chemical properties and measurements of relative atomic masses of the atoms, right? At the time when people, over a few hundred years, when people were just guessing that there might be these tiny particles called atoms, and by measuring, say, volumes of reacting gases, right, they were able to determine from this theoretical idea what are the masses of the atoms relative to one another, right? Starting from this huge base of knowledge collected over a few hundred years, then came Rutherford's experiments, both theory and Moseley's X-ray measurements and calculations, which made these ideas that there are particles, there are these positively charged particles inside the nucleus more and more concrete. Okay, until finally, a few years after that, Rutherford, in about 1920 or so, actually, in effect, discovered the proton.